Two-dimensional momentums. Okay, so previously in this class, we have dealt with vectors before. And one of the first times we ever dealt with vectors was, I always love asking this question, and I'll still ask it now, what's 3 plus 4? Because when we talked about what's 3 plus 4 early on in the year, 3 plus 4 is clearly 7. But if we write 3 plus 4 with vectors, we know it could be many, many different answers. And one of our answers was, if I have 3 going this way, and I have 4 going this way, then going start to finish, or what they're equal to, we know that's 3, 4, 5. That's a 3, 4, 5 triangle there. So 3 plus 4 equals 5, which isn't 7, but it's vectors. They add differently because we're no longer in one dimension on the number line going left and right. We're in 2 dimensions. We're going left and right, and we are going up and down. Because momentum is a vector, we can also add momentums together in 2 dimensions. We can actually do it in 3 dimensions, but going from 2 to 3 dimensions, nothing changes there. So we're just going to look at 2-dimension for this class here, okay? And it's this idea of triangles and possibly SOHCAHTOA that we need to start thinking about when we're adding things in 2-dimensional vectors. So we're still going to use basic triangle principles, Pythagorean theorems, trig functions, sine, cosine, tangent, and whatnot. But we're just going to do that with momentum this time. So nothing's really changing from what we've done previously in the year, just now we're using momentum, okay? So let's take a look at a little example of what this will look like. We are on an ice rink, a hockey rink, so that we can ignore friction. We're going to ignore friction for pretty much everything we do in this class, except, explicit friction problems. And what we have is we've got a hockey puck, and it's moving along the blue line. And if you know nothing about hockey, there are 2 blue lines in hockey. One is here, and one is here. It's how they dictate offsides in hockey. But if we have a hockey puck moving along the blue line at 17 meters per second, and this puck has a mass of 0.16 kilograms, if a player then strikes it so that this puck is then traveling directly towards the goal at some new velocity, 32 meters per second, we want to know that if the stick is in contact with the puck for just 1.3 milliseconds, and that's the same as writing this as 0.0013 seconds for time, what is the force acting on this puck? What is the size of the force? And what is that direction? So that's kind of our setup in this problem. That's kind of our diagram. Let's redraw it to help us out a little bit, though. So what we have here, and we're just going to draw this a little bit bigger, we have a puck moving this way. If we want the puck to move directly to the left, what way do you think we're going to have to strike it? If we kind of draw a grid here, do you think we're going to be in quadrant 1, 2, 3, or 4 in terms of the force striking this puck? I got a 4. So in this case here, it doesn't matter really where you stand, but because this has some velocity going upwards, some momentum going upwards due to the mass, we want to strike this puck somewhere in quadrant 3. We want to say, look, if I have some momentum going up, I'm going to add to it some momentum this way, and when they add together, I'm going to get a net momentum, because the black plus the pink is going to equal the blue. Okay, so that's all we're doing there. We're just saying, look, like this makes sense from a physical perspective. If that puck's coming across, I need to kind of not just hit it straight because it'll kind of deflect at an angle. I need to kind of go back into that puck to get it to go straight. Makes hockey a difficult sport. So that's what we're trying to do here. We are trying to say this. If I have a momentum going this way, which is a mass times a velocity, I need to hit it with some impulse, which is a force multiplied by a time. And if I do that, I am going to get it to go this way with some momentum, which is a mass multiplied by velocity. And that's technically v2, and this up here is v1. So let's see what we can get in this problem, kind of setting it up. We know, in this case, that we have the mass of the hockey puck. It is 0.16, I believe. Yep. So know the mass of the hockey puck. It's 0.16 kilograms. And we know the initial velocity, 17 meters per second. This gives us a initial momentum moving along the blue line. 0.16 times 17, 2.72 Newton seconds. For momentum at the end, when it's directly shot on goal, same mass, 0.16 kilograms, times a new final velocity, 32 meters per second. 0.16 times 32 gives us 5.12 Newton seconds. So if we redraw this triangle, this is 2.72. This is 5.12. What would that hypotenuse be then? What would that impulse be then on the hypotenuse? Well, we know the Pythagorean theorem. We know that our two legs squared and then added together will equal the square of the hypotenuse. So what we can say here is that due to Pythagorean theorem, a squared plus b squared equals c squared, we can say that j squared, the hypotenuse squared, is equal to the square root of, equal to 2.72 squared plus 5.12 squared. And then if we want to get rid of the square here on j, then we'll take the square root of everything. So you want to be a little careful about putting this in your calculator. 2.72 squared is 7.39 or 7.4. We add that to 5.12 squared to give us 33.6. And the square root of 33.6 gives us an impulse j equal to 5.80 Newton seconds. That is what j equals. Well, if we know that j equals 5.80 Newton seconds, and we know the amount of time that we've been in contact with the puck, we know that time up here is just 0.0013 seconds, we can say that if j equals f times t, 5.8 divided by the time of 0.0013 will give us the force here. So divide that by 0.0013, and we get something along the lines of 4,460 newtons of force are applied to the puck in order to strike it at the net. So we just did a little Pythagorean theorem with a nice right triangle there to find the impulse. Once we knew the impulse, we could divide it by the time to find the average force. And remember, this is an average force because as we saw in our force impulse graphs, that force could change over time, but on average, this is what it will be. Now, the other thing that is asked in this problem is what is the direction of this shot? This is really something that, however you want to solve it, is up to you. And sometimes the angle that you're asked to do this from could be different depending on how you kind of set it up. But if we just take a look here, we're looking for an angle in this problem. And if our object, if we're looking at this impulse vector here, this blue vector, let's try to find the angle going all the way around from the positive x-axis. That was how we found our polar angles earlier on in the year. Now, finding that angle is a little bit weird, so what might actually be easier for us to do is to find the angle on the inside here and then take 270 minus this interior angle, and that'll give us the rest going over. Because remember, as we go around a circle, we're at 0, 90, 180, 270. So let's try to find that orange angle and then take 270 minus that. Well, to get the orange angle, we can note that on a right triangle, this is our opposite side, and this is our adjacent side. And if we're looking for an angle, we can use an inverse tangent to do that. Remember, TOA is the opposite over the adjacent, and to find an angle, we use an inverse function. So we can simply say that this angle is equal to the inverse tangent, so tangent minus 1, of the opposite, 5.12, divided by 2.72. Make sure you're in degrees if we're using that. So 5.12 divided by 2.72, inverse tangent. We get about 62, and then 270 minus the 62 gives us an actual angle, theta, of 207.97 degrees. And that's if you're going from like the positive x-axis or the opposite goaltender. If you've kind of shifted your view on a hockey rink, you might have a slightly different setup for an angle of what that could be. But just using our standard mathematical principles, that would be the angle that we see in a problem like this. Okay? We're not going to talk a lot about the whole angles in this class. The real thing to think about is, we know what direction we should be hitting it anyways. Let's just try to figure out what kind of impulse that we do have to act on the object. And we did that just with a little Pythagorean theorem. And if we wanted to go get those angles, it's just a little SOHCAHTOA for that. Okay? So nothing crazy here. Nothing we haven't actually done before, except this time we're just mapping out these triangles using momentum instead of just forces, instead of just velocities, instead of just displacements. So nothing crazy about that. This problem is finished. We'll take a look at another problem like this for an example, but this time in a different sport, volleyball. Until then, adios, and take it easy.